All right, good afternoon, everyone. Welcome. My name is Ellen Rathje. I'm a professor here in geotechnical engineering, and on behalf of the geotechnical faculty, I'd like to welcome you to the 2024 Lymon C. Reese Distinguished Lecture. Before we get started, I do want to identify some of our distinguished guests. We have many members from the Reese family here, so welcome. Thank you for coming. And then I'd like to also recognize that we have students from Texas A&M, so thank you for making the long drive. And we may have some Texas State students. All right, yeah, so we are finding that Central Texas is becoming the epicenter, I had to say epicenter, right, of geotechnical engineering. Any other universities represented that I don't know about? All right, great. Well, thank you all for joining us. So as I said, on behalf of the geotechnical faculty listed here, welcome. This is our current list of 7 faculty: Dr. Alexandra Clara Saracho up here in the front, Dr. Shadi El Motar right here. Dr. Gilbert is the department chair, so we never know where he is. Sometimes he's here. I'm sure he'll be here. Dr. Krishna Kumar. Myself, Dr. Ken Stokey, who we all know right there, and then Dr. Jorge Zornberg. Now, many of you are current students or recent graduates, so you know these folks, but many of you attended UT a while ago, so these are the folks that you may remember. So we really do have a rich history of geotechnical engineering here at the University of Texas. Our most recent emeritus professors are Dr. Roy Olssen. Ooh, I need to snooze that update, that's for sure. Dr. Steve Wright, and I thought Steve was going to be here, but maybe we'll see him in a little bit. But look at the names that are here: Priscilla Nelson, Dave Daniel, Roy Olssen, and Steve Wright, Hudson Matlock, Lyman Reese, of course. And then it really all started with Raymond Dawson, probably almost 100 years ago. And if you want more information about the history of our program, there was a time Terzaghi was here and interacted. It's all on our website. I did want to identify a few highlights from the last year in 2023-24. You may have noticed that our department has a name now. So we are now the Faribault-Massey Department of Civil, Architectural, and Environmental Engineering, due to a generous gift by Dr. Massey to really transform our department and push civil engineers to be engineering the solutions for our global problems. He calls it engineering the big. And we really went all out at the naming ceremony. We had the cheerleaders, we had Hook'em, we didn't have Bevo, that would have been a little dangerous. We did have the marching band, however, sang the Eyes of Texas right there in the atrium where you were at. So you can see, look at the number of people in the EERI, I always say EERI, I don't know why, the EER atrium next door. So it's really a great event, and so you'll be hearing more and more about that over the coming years, how this gift is going to transform our department. Other more local highlights: we just were able to recognize Dr. Zornberg with his Peck Lecture at the Geo-Congress in Vancouver in February, so that was a great event. And in the fall, we celebrated 50 years of Ken Stokey at the University of Texas. So it was great to recognize Ken. His family was here. All his grandkids were here. I think all the grandkids were here. And we even had a visit by Roy Olssen, which was wonderful. If you're here, you likely are part of what we like to call the Longhorn geotechnical family. And one of my favorite things about going to Geo-Congress is to see so many of our alumni. And so these are pictures from the last couple of Geo-Congresses, seeing so many folks that have been here through the years. And as I like to say, you can check out any time you want, but you can never leave. Okay, so once you're a Longhorn for forever. Tomorrow we'll be having the Reese golf tournament, and so there's a picture of Dr. Reese from back in the day when he was golfing, and he was loved golf, and that's why we have the golf tournament. And we will see who will win the tournament tomorrow. So how many golfers do we have? We have about 30 golfers tomorrow. I know. Most golfers are going to be, but you only need to watch in the afternoon, right? I mean, on the weekend. What? Yeah. So a couple of years ago, we created a new award, the Roy E. Olssen Award, and I'm going to invite Krishna Kumar up to announce the award winner.
Yep. Hello, I'm Krishna Kumar. I'm an assistant professor in geotech, and we created this award to honor Professor Roy Olssen, and this is to honor our graduate students. So we've been doing it for several years now. So we considered all the students started in the academic year 22-23, and this is to identify, highlight a student who has done excellently in their academically, and also contributed to a vibrant geotechnical community at UT. So this year, award goes to, so drum rolls, please. Ashish Govindan. Hi, Ashish.
We have to get a picture. All right, thank you. So before we move on to the lecture, I always like to take a little bit of time to talk a bit about Lyman Reese, because most of particularly the students here, didn't know Lyman personally, and I really think he has a very compelling life story, and we're going to hear from his family with some more personal tidbits. But I just wanted to hit some highlights about Lyman, the person. He was retired when I arrived here in 1998, but he was such a kind soul to me, would come in and lecture and give a guest lecture for the undergraduate foundations engineering class. So it's really interesting to see, though, where his life started and then where it went. I mean, he was born in Southwest Arkansas, but a very modest family, hardworking. He grew up during the Great Depression, which made things very difficult, of course, for many people. At some point, they moved to Texas, and that is in Abilene. That is where he started caddying, and that's where his love for golf started as he was caddying in Abilene. He was the salutatorian for his high school class and started at Abilene Christian College. But because of financial difficulties in the family, he had to give up college to help make money for the family. He became a land surveyor. He ended up in the Seabees and served as a chief petty officer in the Aleutians in Okinawa. And then at the ripe young age of 29, he started at Rice University as a freshman. How many people today start college when they're 29? Not too many, but those were the circumstances. His first semester, he did 22 credit hours, also lettering on the golf team. But he did transfer to the University of Texas shortly thereafter because it was more flexible, the coursework that you could take at UT versus at Rice. And it's important he transferred to the University of Texas because that's where he met his wife, Evalie. So that was a great decision for him in many respects. Beyond also getting his bachelor's and master's degree from UT, going to Berkeley to get his PhD, and then coming back to teach here at the University of Texas, where he had a long career of, I believe, 33 years. He was elected to the National Academy of Engineering in 1975. He gave the Terzaghi Lecture in 1986. He became an honorary member of ASCE in 1984 and retired from UT in 1988. And after then, he didn't just relax, he started company, Ensoft, and Lyman C. Reese Associates, which is still in practice today. And you'll see that they've been a sponsor of this event as well. So I'd like to invite John up to talk, just to tell a little story about Professor Reese.
Good afternoon. So this story is actually composed by my sister, who's not here today, but it's about a 36 Ford. All right. Our dad, Lyman, was born in a boxcar in Arkansas during the Great Depression, where his father worked as a logger. At a young age, his family moved from Arkansas to Abilene. While in high school, my grandfather, Daddy's father, passed away, so he began working as a golf caddy after school and on weekends to help his mother make ends meet. He graduated high school, salutatorian, and attended Abilene Christian for 1 year, but as she said, didn't have enough money to continue. So he went to work in South Texas as a surveyor, and World War II caught up with him, and he joined the Seabees, building and surveying military bases in the Aleutian Islands in Alaska. After World War II, his dream of studying engineering finally came to fruition. He attended Rice University on a golf scholarship and later UT on the GI Bill and earned his bachelor's and master's degree. He also met and married our mother, a nurse who was also getting a master's degree in nursing education. So, getting to the Ford. It was the only vehicle our parents owned in the early 1950s, and it was pretty much worn out already. In fact, Daddy used to carry a spare fuel pump, and the fuel pump went out so many times that he got to where he could replace the fuel pump on the road in 10 minutes or less. So the fuel pump would go out, he'd get the new one out and get it put in and keep going. We lived in Starkville, Mississippi, where Lyman was an assistant professor at Mississippi State. He wanted to get his PhD, and he wanted to come back to Austin to teach at UT. So during the 50 to 51 school year, he won a one-year fellowship from the Rockefeller Foundation. He made the decision to go to UC Berkeley for his PhD. So we loaded up the old Ford. I was 1 year old, and my sister Sally was 2, and headed out to California on a wing and a prayer. They drove over mountains, through the deserts, had very little money, and we didn't know where in the world we're going to end up, where we're going to live. He had to kind of go on faith, okay? The trip was momentous, to say the least. When they arrived, they were told that they would be living in housing that the shipbuilders had used in World War II, which UC Berkeley had recently acquired. So they drove the car around. Let me see, I'm going to skip that part. So the first Christmas at Berkeley, they couldn't figure out what to get us, Sally and myself, for Christmas. Well, Daddy went to the thrift shop and found an old tricycle, and it wouldn't work, but he oiled it up, got it back together, and painted it, and so that was our present for that Christmas. We shared the tricycle. Someone in the housing project stole the tricycle within 2 weeks. So that was our first Christmas there. So a few months later, they were going to build us a sandbox to replace the tricycle, and he made the frame out of wood, took the Ford to the beach and filled it up with beach sand so he could bring it back for the sandbox. The problem was the sandbox was a big success, but within a few weeks, somebody had stolen all the sand out of the sandbox. So let me skip on down. 1955, we headed the old Ford up and came back to Austin, where he took a position as assistant professor here at UT. He began research based on work according to his dissertation. He had support at the time from the petroleum industry, the Federal Highway Administration, and NSF, and led to publications of numerous articles on deep foundations. He was promoted to full professor in time, became chairman, department of the chairman, associate dean of engineering, and later a funded chair. He was elected to the NAE, National Academy of Engineering, won many awards, presented at conferences, so forth and so on. Okay, what happened to the Ford? A year or so after moving to Austin, mother wanted to go out to Lake Travis on a picnic. Anybody ever been out 2222 going to Lake Travis? Really steep, right? So we got started, and the old Ford wouldn't go. It would not go up the hill. So he came back down, let it cool off a little while, tried to go back up the second time. So finally we had the picnic at the bottom of the hill. Okay, so let me just read a little snippet that I had come up with on my own. Forgive me. Daddy lived his life in pursuit of knowledge. He wanted to make the world a better place. He wrote books to pass down that knowledge for future generations. He was very concerned about the engineering profession. And he didn't have it easy in his life. He was raised, as you've heard several times already, during the Great Depression, and had to work hard to support his mother after his father died. And you know, I couldn't believe it, but he used to save like this much out of a meal. If he had one bite left, he would put it in the fridge and save it, wrap it up. And that's what happened when you lived during the Great Depression. I mean, you were looking for something to eat. So I'm sure he would want me to tell you, pursue your dreams, work hard, don't give up. The world needs good engineers, and hook 'em.
Thank you so much, John. And now you know where my information came from, because at least our stories were straight. So, but that was much better told. So thank you, John. So a last few slides about supporting our program. We've talked about this before. We have the Lyman and Evalee Reese Endowed Excellence Fund, as well as the Roy Olssen Professional Endowed Excellence Fund in civil engineering. And these funds allow us to support various activities with the graduate students and continue that vibrant community that we have. So if this QR code will take you to the Geotech website, and to the page where you can donate electronically. But if you have any questions, email Ken Stokey and he'll email you right back, I'm sure. I mean, Alicia will. All right, so now as we prepare for the Reese lecture, we've been fortunate for many years, and I realize that we started in 2006. So we're not quite to 20 years, but we've had a good run, and Fugro has been our foundational sponsor since the beginning. So I'd like to welcome Thalia Travasoro from Fugro to say a few words.
Hi, good afternoon, everyone. It's great to be here again. I was actually here 3 weeks ago visiting with this department, and I'm coming from the West Coast. It has started feeling, it's frequent and I enjoy it so much, it has started feeling like family. So like I'm part of the Longhorns. Let's see, so I'm Thalia Travasoro. I'm Fugro's technical director for our land business in the Americas region. And Fugro has been a sponsor of this event for 18 years now, so I get to stand up for a couple of minutes and tell you something about the company. First of all, I want to welcome you in this distinguished lecture series to celebrate Professor Reese's lifetime achievements and his service and legacy, and welcome Dr. Bonaparte in anticipation of his lecture. So like Professor Reese has been a pioneer in the field of the foundation design, Fugro has been a pioneer in the field of geodata and geotechnics. The company was built back in the 60s around a novel concept at the time, or a tool, the CPT, and the idea that this tool could be used to deliver superior foundation design, which we started doing in the next years and for decades later. And we have been able to gather geodata, interpret such data to help build and maintain project structures on sea and land around the world. But we live in a very dynamic and fast-paced world, and things are changing around us. We see significant population growth, climate changes, urbanization, and these pose challenges that as geoprofessionals we need to think through thoroughly and provide solutions. So our company, my company, has been reinventing itself in the past 5 years or so, and we're now using our geodata expertise and geoservices expertise, our many innovations and technologies, our expertise, people's expertise, to deliver solutions to address these new challenges. And I have been part of this journey and very proud to do so. And I was very excited to see Dr. Bonaparte's topic for his lecture today, aligning so well with my company's vision, and really waiting, very eager to see the insights that you are going to share with us about how to be leaders as geoprofessionals in developing solutions for the climate change-related problems. On a more personal note, I want to say that, so I'm a UC Berkeley graduate. I did my PhD back at UC Berkeley back in the day, and when I was about to graduate, Dr. Bonaparte was invited to deliver a keynote lecture at a similar event at UC Berkeley, and his topic at the time was what a career as a geoprofessional looks like. And I was about to graduate. There was quite a bit of uncertainty in my life. Didn't know, what path to take. And it was a truly inspirational lecture, one of the best that I have seen in my life, and very much motivated me to pursue the career that I have pursued today. So I have been feeling a bit shaky and uncertain lately, and I'm really looking very much forward to your insights and another inspirational presentation sharing insights and guidance on what as geoprofessionals we can do for the future. Thank you, and join me in welcoming Dr. Bonaparte.
Okay, I promise. I only have 22 more slides till we get to the presentation. This year we did open up sponsorships to other companies. So if you want your company's logo up here next year, come talk to me. But NSoft, Keller, Geosyntec, and Terracon graciously also provided support. And the support that the Reese lecture sponsors is used for, we use those to better support this event, but also to further the activities we can support with our graduate students, such as sending them to Geo-Congress so that they can continue to initiate their beginning in the geotech family of the University of Texas. And then last, we do have some golf tournament partners, NSoft as well, Geotech, Steve Troutwine's company, and Jonathan Motherwell and Grant Thompson also contribute. And these funds help defray some of the costs for the students playing in the golf tournament tomorrow. Okay, without further ado, I'm going to invite Jorge Zornberg up to introduce Dr. Bonaparte.
Dr. Bonaparte, Rudy, it's such a privilege to have you back at UT Austin. Dr. Bonaparte is board chairman and senior principal at Geosyntec Consultants. He's also a professor in practice at Georgia Tech, and he was for 20 years the president and CEO of Geosyntec Consultants. But let me tell you something unique. So Rudy is someone that thinks extremely creatively has a very innovative thinking. But Rudy, no offense, but that's not what sets you apart. What sets Dr. Bonaparte apart is that he can translate that creative thinking into concrete major achievements in our profession. And that is what sets him apart. Now, we heard about Dr. Reese, his humble beginnings, and I must tell you, it was not always rosy for Dr. Bonaparte. He had some financial hardship, and in his words, he was a C- student in high school. And he realized that to help his family, he could not get the jobs that he needed with being a C- student, and he had to buckle up and do something better. And he did so much better that he was admitted at the University of Texas at Austin, 1973. And he did so much better that he graduated as the outstanding graduate of the College of Engineering in 1977. Well, then he continued to Berkeley to get his master's and PhD under the mentorship of Professor Mitchell. And, well, some of you may not know that we owe to Dr. Bonaparte as much as we know about a very special clay, the San Francisco Bay mud, that at the time was very unknown, we had a very unknown behavior, and now his tests from many years ago continue to be the reference and being used in homework assignments. But that's when probably his creative thinking started to be translated into enormous achievements. He was hired by a very obscure startup firm that now we know as Tensor Corporation. And under his initial leadership, Tensor became the leader in geogrids that we have right now. And someone had already met Rudy, and that was J.P. Giroux. And he was starting another company called Geosyntec Consultants, and they managed to snag Rudy out of Tensor. And as I understand, you are employee number 1. And under his leadership, Geosyntec became from being a one-employee firm to being a 200-employee firm, which is when I joined Geosyntec, to become now a 1,200-employee firm in over 7 countries and 60-plus offices. So this is an enormous achievement, and you are all benefiting from this, because while he was working at Geosyntec, I was in the Huntington Beach office, he was in the Atlanta office, but we all benefited from the knowledge that he was bringing. From your homework assignment, you would know whom to credit for the equation for leakage through geomembranes, and the equation for the leakage through composite liners. And when we go to the equations to breach a void, that all comes from Dr. Rudy Bonaparte. So his professional practice has focused on the design of environmental cleanups for contaminated sites and waterways. And he is the recipient of many awards, including some very distinguished ones, the ASCE Terzaghi Lecture Award. One that is particularly impressive, I found particularly impressive, that is the ASCE Opal Lifetime Achievement Award for Design, the Cross Medal from ASCE, and he was elected to the National Academy of Engineering in 2007. And he's very generous. He has served our department well. He served as an CAEE External Advisory Committee, and he was elected to our Academy of Distinguished Alumni. So, Rudy, with such creative thinking, and everything that you touches is transformed into great achievements, I'm really looking forward to see the great achievements in a very big challenge, which is climate change. So, looking forward to that.
Well, Jorge, thank you very much for that kind introduction. It was too much. And Thalia, if I made you nervous, you made me nervous. So we're even now. The title of my talk, as you can see, is Geoprofessionals and more broadly, all CAEEs as leaders in climate change, mitigation, and adaptation. And when I thought about this talk, I thought about talking about things I've done in my career, but instead decided to look forward to the future and the way I see climate change and the way I see it affecting our profession. And I thought the audience was really targeted towards students and early career professionals, and I'm excited to see that there are a lot of you students and early career professionals from Texas A&M and Texas State, because this is going to be a very big deal during the time frame of your career. I want to say that UT Austin had a tremendous positive influence on my life, and I owe a debt of gratitude to many, but especially to Roy Olssen and Lyman Reese. Roy was my undergraduate advisor, mentor, and friend. He helped me enormously. He really did. I don't think I would be here today if it weren't for Roy Olssen, and I truly mean that. I'm not just saying it. And Lyman wasn't my advisor, but he was always very kind to me and supportive and made me feel good about being in the program and about myself. And I've never forgotten that. And I know now that he's a great man, and I always knew he's better than me, but I now know he's even more better. When Jorge talked about my C- grades in high school, what he didn't mention, maybe didn't know, is my dad passed away when I was a freshman in high school, and I worked 5 nights a week as a janitor from 6 to 10 o'clock at the high school I went to, which really wasn't very good for my image, but it threw me off in terms of academics, and I didn't do well, and I was really, it was really great to hear about Lyman, working to help support his family and at the same time being such a great student. It took me a lot longer than it took Lyman. These are 2 wonderful gentlemen, 2 great professors, 2 people that had a really substantial impact on my life. There's an important nexus of my lecture to the vision for UTCAEE, and I'm not going to say CAEE again. It just doesn't roll off my tongue. So I'm just going to call it CE. And when I say CE, I mean the whole kit and caboodle. So let me put on my glasses. The department has a vision, a recent vision statement, and it's worth reading. UTCE faculty believe that the complex problems surrounding the nexus of cities, water, and energy, will challenge CE for decades to come. And we being the faculty, aspire to be leaders in developing innovative solutions to these problems. So that's your vision. Bob Gilbert, your department chair, said CEs can lead in addressing, quote, the big problems of today: climate change, limited resources, outdated and crumbling infrastructure, and many more. And your benefactor, Fariborz Massey, simply said, engineering the big. And that, I think we can all visualize what's meant by that. So this lecture, climate change has the potential to greatly impact society. We all know that. It magnifies, and I want to stress that, it magnifies the complex problems between cities, water, and energy. And it will involve engineering the big, as we will see, to mitigate its effects and to adapt to it. So that's the connection of this lecture to this program. The outline for my lecture, a little bit of background information. Then we'll look at climate change impacts on Texas and the Gulf Coast region. I think many of you know that. I only have a few slides to address that. And then contributions that UT Geoprofessionals, and more broadly all CEs from Texas A&M, Texas State, and anywhere else that's represented here today, The contributions that we can make to climate change adaptation, and we'll look at that first. Climate change mitigation, we'll look at that first, and then climate change adaptation and resilience, and then I have a few takeaway messages. So the 2024 scientific consensus, Earth's lower atmosphere has warmed about 1.1 degrees C, that's about 2 degrees F, above the 1850 to 1900 baseline period, primarily due to anthropogenic greenhouse gas emissions, most notably carbon dioxide, as we see on the NOAA figure on the right. This past year was the hottest on record, 1.4 degrees C of warming during 2023. That may have been impacted by El Nino, we'll see in the coming years. And we know that there's more warming over land compared to over ocean, so if it feels really warm in Austin, Texas, it's because it's really warm in Austin, Texas. A warmer Earth is changing climate patterns with impacts at the Texas Gulf Coast, US, and global scales. Unfortunately, the world's struggling to reduce those emissions, notwithstanding national pledges to do so. We can almost say we're failing. Consequently, continuing high greenhouse gas emissions will cause more global warming for decades to come, resulting in more frequent and severe impacts. This is a really striking plot from the U.S. Energy Information Agency. It's projecting energy consumption globally, around the globe, not the U.S., through 2050. And you don't see any of these curves going down. Globally, EIA projects that by 2050, the world energy demand will increase by about 20 to 50%. So we need a lot more energy as a society, and there's a whole variety of reasons for that. Population growth and a lot of other things. In the plot, renewables, the green line, will grow quickly, and it's interesting. It'll meet most of the new demand for energy in the world in the coming 30 years. So you can see the slope on the green line. At the same time, there's this current existing baseload of energy that's needed, and what we see is that fossil fuels will continue to be needed to meet those energy demands. And in fact, the growth in natural gas and oil will be slightly positive during that time. So anyone that thinks the oil and gas industry is going away in the next 2 or 3 decades, it's just not going to happen. And on the one hand, that creates a problem with respect to global warming. On the other, we're in Texas, and I don't mean this as a joke, but this is the economy of Texas is highly tied up with that. So that's a helpful thing to the state and all the people that work in that agency, that work in that area. So without transformational breakthroughs in carbon capture utilization and sequestration technology, CCUS technology, and deployment of this technology at massive scale, and that's really the important thing, deployment at massive scale, it seems inevitable that global warming will blow past 1.5 degrees C, the IPCC Paris Agreement goal, and likely exceed 2.5 to 3 degrees C in this century. Let that sink in. That's a lot of warming that's going to have a lot of impacts. So the question then is CCUS today up to the challenge? And the answer is no, it's not. And that's not meant to be a negative comment about CCUS. It's a comment about the state of technology development and deployment. If we look at things like direct air capture, clean energy, carbon mineralization, putting reflective materials in the atmosphere, putting absorbent materials in the ocean, these are all really promising technologies, but none of them are at a state of development or a state of deployment that will bend the curve in the next several decades. So that leaves us with more conventional carbon capture and sequestration from industrial sources and then deep geological sequestration. So where are we with this technology, which perhaps gets the most interest and press? So as of 2022, global CCS capacity was 42.5 million tons per year. And that may seem like a big number, but it's only about 0.1% of global greenhouse gas emissions. If we look at projects in the pipeline and earlier advanced development, that represents about another 0.5%. Not very much. That's not going to bend the curve. In modeling by IPCC and others, CCS capacity needs to grow to 7 gigatons per year by 2050, along with a whole bunch of other things. So we need that much CCS with a whole bunch of other things to support a 1.5 degrees C climate scenario. And so in thinking about this, remember that CCS project development timelines from planning, permitting through construction and commissioning are 7 to 10 years or more, a decade. So you put all of this information together, and what's your conclusion? There is insufficient time and insufficient investment for CCS to meet the 7 gigaton per year goal by 2050. It's not even close. So to wrap up this background, a few key takeaway messages before we move on. We're on a trajectory where the world will continue to burn fossil fuels at a high rate through at least 2050 to meet global energy demand, notwithstanding the large contributions of new energy capacity from renewables, as we saw on the EIA plot. The trajectory for CCUS deployment, as I just talked about at scale, is too slow to prevent average global temperature increases of at least 2.5 to 3 degrees C in this century. And that's a global average. It will be higher over land, it'll be higher in some parts of the US, it'll be higher in the Arctic and in other places. And in the Arctic, it has huge geopolitical consequences. Nonetheless, I don't want you to think I'm here to bash CCUS or clean energy technologies. I think it will become vitally important over the longer term, and I strongly support national efforts to develop these technologies, as I do development of non-carbon power sources, including renewables, advanced nuclear, hydrogen, and fusion. It's just going to take longer, and we need than we would ideally like, but we need to recognize that and not pretend we're going to get there. So that's the background. I went through it quickly. Climate change impacts on Texas and the Gulf Coast. Here are 25 current impacts that will grow over time, applicable to the United States. Most are applicable in this region of the country. This is from the 2023 Fifth U.S. National Climate Assessment. I'm not going to go through these. I'm not going to read this list. I'm just going to pick out 5, and I have one slide on each to touch on before we look at mitigation and adaptation. Well, the first projection is more extreme precipitation amounts that will occur at greater frequencies. In the figure on the left, from the Office of the Texas State Climatologist, you see the change in frequency of the 100-year 24-hour storm since 1960. And you can see that there have been large increases in the frequency of that storm in the last 60 years, particularly in the eastern part of the state. I've highlighted, for example, Harris County, where the increase in storm frequencies on the order of 30 or 40% already. And the state climatologist is predicting increases of another 15 to 20% by 2036, which is 12 years from now. I don't know why they picked 2036 for the projection. It seems a bit odd, but that's what they picked. And that frequency will continue to increase with time. The biggest driver, I think, as we all understand, for this increasing precipitation is increasing evaporation with a warmer climate, leading to more moisture carried in the lower atmosphere. So that's one projection, more extreme precipitation. This next projection is associated with that, in fact, a consequence of that. That's more frequent Gulf Coast extreme precipitation flooding. So we all know we can't attribute any particular storm to climate change, but we do know that the probability of such storms and the intensity of such storms, those probabilities are increasing. So it becomes more likely that you will have more storms in the future in Texas, like Jamaica Beach in 2021, where 14 inches of rainfall fell in 24 hours, or Dallas, Texas in 2022, when 15 inches of rainfall fell in 24 hours. So more frequent and more intense rainfall events. It's coming. It's already here. Third area of projection, really significant, sea level rise. And these are plots for sea level rise, relative sea level rise. Relative sea level rise includes subsidence of the ground surface, which is a factor along the Texas Gulf Coast. For the eastern Gulf on the left-hand figure and the western Gulf on the right-hand figure, let's just look at the western Gulf for a moment. And you can see, if you look at this, these are projections from NOAA, that by 2050, relative sea level rise in the Western Gulf, which includes Texas, will be 18 to 24 inches higher than 2000 levels, about 6 inches higher than both the national average and the Eastern Gulf Coast. So that's a lot of sea level rise, very significant sea level rise projected in the coming 20 to 30 years. That's through 2050. Does sea level rise stop after that? The answer is no. Sea level rise lags behind temperature increases in the environment, so we're going to continue to see sea level rise for a very long time. And in fact, the same NOAA projections are shown here. And I should have mentioned when I started, this is for an intermediate climate scenario, so I didn't pick a worst case. This is for what I think is likely and is consistent with the 2.5 to 3 degrees C temperature rise in this century. And so these are pretty remarkable numbers. By 2100, relative sea level rise along the coast will be 1.6 meters or 5.2 feet. And by 2150, 2.8 meters or 9.2 feet, almost the height of a basketball goal. So you're an engineer, you're working on adaptation measures, you're working on a design for a highway structure, coastal defense structure. What do you design for? Do you design for the 2050 projected sea level rise, 2100, 2150? These are really big questions, really important questions that we need to consider when we look at designing to address this. So what does a 3-degree increase in global average temperature look like for the Western Gulf Coast? These are projections of inundation at mean higher high water with 3 degrees C warming by 2100, absent adaptation measures. And this is from IPCC 2021. And you can see the areas around New Orleans, very large areas that will be inundated for this scenario, which I think is a realistic scenario. Western Louisiana, Eastern Texas, Port Arthur, Galveston, and the South Texas shoreline, very significant areas. You look at this and you say, there will be a need for enormous amounts of engineering work to adapt this part of the world to these conditions. Another projection, more intense Gulf Coast hurricanes. Based on a 2021 meta-study, NOAA concluded increasing ocean surface temperatures are likely to fuel more powerful, that is category 4 and 5 hurricanes. And I underline the word likely because that's defined in their reports as a confidence level that scientifically this is the right conclusion. So scientifically, this is likely to be the case. That's a high level of confidence. Due to more moisture in a warmer atmosphere, about 7% more moisture per 1 degree C of warming, hurricane rainfall amounts are likely to increase. Again, a high probability that this is the right scientific conclusion. So it's more likely that in the future, we'll see events like Hurricane Harvey in 2017 that dumped over 50 inches of rainfall in some isolated parts of the Houston area. The destructive power of hurricanes will be amplified by sea level rise. And hurricanes may, so this is less scientifically certain, move more slowly in a warmer future. More intense Gulf Coast hurricanes. One last projection. Drier West Texas soil will increase the need for farmers to irrigate their crops, leading to increased groundwater withdrawals and reduced river flows. So you may know that in the Texas Panhandle and West Texas Plains, most irrigation water is groundwater, and it comes from the High Plains Aquifer, also called the Ogallala Aquifer, which is shown on the figure on the left-hand side of this slide. The aquifer has been in overdraft for decades. I think it was in overdraft when I was a student. It's been in overdraft for decades, since the 50s, so it was when I was a student, I remember studying that. The amount of water stored in it has declined by more than 50% in some parts of the state. And the areas in red shown on the slide are those that have declined by 50% or more. Groundwater is presently being pumped for irrigation 10 times faster than it's being recharged from rain and snow, so it's going to continue to be drawn down. Worsening overdraft and diminishing supplies are projected for the coming decades, creating even more stress on the aquifer. And we'll see a little later how civil engineers, how we are going to have to help with the solution to this through adaptation measures in water supply. So that was a quick view of just a few of the impacts of climate change that are here already and that will become more significant in the coming few decades. Let's look now at the contributions that UT, Geoprofessionals, and more broadly all CEs, including all of those here today from Texas A&M and from Texas State, the contributions that we can make as leaders to climate change mitigation. I've listed here, and I don't expect you to read all this, and as an aside, at the end, I have my email address. If anyone would like a PDF of this presentation, I'm happy to send it. Areas of national efforts to mitigate climate change and global warming. And by mitigation, what we're talking about is reducing, capturing, and/or removing from the atmosphere greenhouse gas emissions. So having less carbon in the atmosphere. These 10 areas, as I've already described, some of them will be important in our future, but maybe not so important in the next several decades. And that doesn't mean they're not needed. It doesn't mean we shouldn't be working on them, but they're not going to bend the curve in the short term. Nonetheless, we need to do what we can as engineers, as responsible engineers and citizens. I've identified 4 here that are highlighted that I think are the areas where we as CEs, geoprofessionals, environmental, water resource, all kinds of CEs, can make the largest contributions. First, increasing the use of renewable energy. Second, improving the energy transmission and distribution grid. Third, increasing carbon capture and sequestration from point source emissions. And 4, reducing carbon emissions. And we'll look very briefly at 2 areas, transportation and buildings. Well, first, mitigation by increasing renewable energy capacity. Today, 18% of electrical energy generation in the country is from wind and solar. That's a significant percentage, and as we saw on the previous plot, it's going to increase very rapidly in the coming years. It's going to be a big contributor to taking up new energy demand. Texas by far leads the country in wind energy development. In fact, Texas has something like 15,000 wind turbines around the state, and collectively they have a peak generating capacity of 40 gigawatts, 40,000 megawatts. That's something like 20 nuclear reactors. So it's a lot of capacity, large nuclear reactors. We see in the photo in the lower left the 780 megawatt, which is big. That would be a very large, for example, coal-fired or oil-fired power plant. Roscoe Wind Farm complex, and in the upper left, a map that shows the locations of the 10 largest wind farm projects in the state. And you can see that much of the capacity is centered in the lower Panhandle area in South Texas, both excellent locations for sustained wind energy generation. So this is a little dense, but bear with me. How can we contribute to projects like these as CEs and specifically as geoengineers to onshore and offshore wind, solar, hydro, and geothermal. And I've listed some of the ways here. Siting studies, environmental impact studies, water resource investigations, hydrologic and watershed studies, a whole bunch of other things. Then go on, geological and geotechnical investigations, faulting and earthquake studies, extreme load evaluations, hurricanes, foundation and structural design, design of site civil infrastructure. It's monotonous to read that, I know, but I want to make a point that there are numerous ways that we, all of us in this room, can contribute to renewable energy projects. A recent example that we were involved in, this is finite difference performance modeling for wind turbine pile group foundations in Texas. Part of the reason I'm showing it, we did the analyses using the NSOFT program group, and as we heard from Ellen a little earlier, NSOFT was founded by Professor Reese here in Austin, Texas. And just another example, some Plaxis 3D finite element performance modeling for wind turbine post-tension concrete pier foundations. This is for a site in Oklahoma. So examples of specifically geoengineers contributing to these types of projects. The second area of mitigation is improving the nation's energy grid. So if you think about it, there's all this new renewable energy coming online from hundreds of sites located all over the state, all over the country, not just from concentrated power plant sites where you can run a transmission line fairly simply. So how do you take distributed energy from this renewable energy, from battery storage projects and other things, and put it together into a cohesive electrical transmission grid? Doing that, recognizing that the current grid in most locations is more than 50 years old. So this is an enormous need for the country, and it's a big deal, and it's one of the greatest limitations on the implementation of renewable energy. The U.S. Department of Energy Berkeley National Lab indicated about a year and a half ago that DOE has more than 5,000 applications from renewable energy projects and battery storage projects to hook up to the grid, and the list is growing faster than they can take projects off it. So there's an enormous need to connect this new energy to the grid, and we're struggling as a country to do it. So we, as civil engineers, can contribute to these types of projects. Here's an example, the Sunrise Power Link renewable energy transmission line in Southern California. This is a project that involved a 17-mile long high voltage transmission line from Imperial County in the arid part of southeastern California to San Diego County near the coast. And all the energy being transmitted along this line is from wind and solar energy. And you see the route of the line and a few photographs and things. But again, there are enormous ways that we can contribute to a project like this, and I'm not going to read this list. Just two or three things that are kind of unique to a project like this. The corridor routing studies and planning for transmission lines, corridor natural hazard studies, something that geoengineers lead, faulting, landslides, karst, stream crossings, and then all the other things that you see here. My point again, and I'll make this point several times, we as civil engineers can make large contributions in the area of climate change mitigation. Another example is mitigation by carbon capture and sequestration. This is a project in Louisiana that's in the permitting stage, the Blue Sky River Parish Deep Sequestration Project, where when fully permitted, will over its life involve the injection of about 400 million tons of CO2 way deep beneath the ground. The project is illustrated on the left-hand side graphic, where you see that this is along the Mississippi River. CO2 will be gathered from industrial facilities that are shown in the graphic, conveyed through a network of pipelines, which are shown in purple, to 7 deep wells that will inject the CO2 into permeable sandstone strata up to 11,000 feet deep, illustrated on the figure on the right-hand side. You might ask, how can we contribute to this type of project? Once again, it's a long list, not going to read it. The point again being that there are many ways to contribute. I'll mention just one. That's the third bullet down. These projects require a lot of permitting. There's something called an EPA Class 6 deep injection well permit, and that has a lot of aspects to it, including requiring geological and geophysical investigations, faulting, fracturing, and subsidence studies, induced seismicity studies, and subsurface CO2 transport modeling to make sure you know where the CO2 is going to go and what it's going to do. So I think you get my point again. Mitigation in the transportation sector. We see on the left-hand side the pie chart that shows that most CO2 emissions in the sector come from light-duty vehicles and medium and heavy-duty trucks. And as CEs, we're not involved in mitigation related to vehicle fuel efficiency, non-carbon fuels, and electric vehicles. That's the domain of other types of engineers. But when we do a transportation project, it's often the case that one of the benefits of the project, amongst multiple benefits, is a reduction in greenhouse gas emissions. Now, that might not be the case here in Austin with the expansion of I-35, which I understand is a bit of a controversial project, but there are many types of projects that we do in the transportation sector that lead to the reduction in greenhouse gas emissions. And again, I've given a list, but studies, things like debottlenecking studies and ridership and routing planning and those kinds of things. Clearly, you're trying to improve the rider experience, you're trying to decongest the roadways, but those things lead to less greenhouse gas emissions. And then studies, engineering, and design. For example, Texas is working its way along very, very slowly, I think, towards high-speed rail between Dallas and Houston. Well, one of the benefits of a project like that would be a reduction in greenhouse gas emissions because the high-speed rail is less of a carbon emitter than all the cars that drive back and forth between those two locations. And many other things like urban trolley, light rail systems, bus rapid transit systems, multimodal transportation hubs, and so on and so forth. So you might not think about CEs being able to contribute to mitigation in the transportation sector, but indeed we do. And finally, mitigation through sustainable and energy efficient buildings. I'm illustrating this with two buildings on the left-hand side on the Georgia Tech campus. Buildings I walk by when I'm going there to teach. The Engineered Biosystems building in the upper left, it's LEED Platinum certified. And the Candida building for innovative sustainable design in the lower left, a really striking building when you see it in person. Once again, we contribute in many, many ways. Energy efficient structural building envelope and foundation design, energy piles, low impact site civil design, green roof, rainwater harvesting, specifying local and recycled materials, again, and so on and so forth. Gray water treatment systems, black water treatment systems. When you actually look at it, there's a lot of ways that we contribute in these areas. So we just looked at a few areas of mitigation that we as CEs can contribute to. And it looks like we can make a pretty significant positive impact in that area. We can be very helpful in that area. And if that is the case, when we compare it to adaptation, we are in a position to make an even bigger impact on the adaptation side, on adapting infrastructure, the environment, society to the effects of climate change. So let's look at that. Here's a partial list. I don't expect you to read it, but I put it up to make a point. The need to adapt our infrastructure and environment to the effects of global warming span just about every aspect of infrastructure in the environment. And I've indicated here that there's a role for civil engineers, civil and environmental engineers, and in most cases, geotechnical engineers to make contributions. And these are all big areas. This is engineering the big, for sure. And most of these, or many of these, are at the nexus of cities, water, and energy. So, adaptation projects related to this are needed by society, and they're entirely consistent with the vision for UTCE. I'm going to just touch on a few that I think are important in this part of the world. Adapting coastlines and coastal cities for sea level rise and storm surge. Adapting existing and future floodplain areas for increased flooding potential. Adapting for increased scour and erosion potential along streams and rivers. Making transportation systems more resilient to sea level rise, storm surge, and flooding. Protecting previously closed coastal hazardous waste sites from sea level rise and storm surge. And protecting and expanding water supplies due to increasing populations, that's one of the drivers, increasing drought and diminishing groundwater supplies. So there's a lot of drivers on future water supply. So let's start with adaptation for sea level rise and storm surge. This is the Greater New Orleans Flood Protection and Risk Reduction System that was developed after the impacts of Hurricane Katrina in 2005. This was led by the U.S. Army Corps of Engineers and involved major civil works. I've highlighted just two of the projects on the right-hand side, the West Closure Complex and the Lake Borgna Surge Barrier. Geoengineers led most of this work, along with other types of civil engineers. But we made, as a profession, enormous contributions in this area. We can be very proud of a profession of the benefits we help bring to this part of the country. I think you would agree with me, this is engineering the big, and I think you would agree with me, this is working at the nexus of cities, water, and energy. And Louisiana isn't done. You might say, well, I'm a young engineer and all that work is done, so I won't participate in it, but that's not the case. There's something called the 2023 Louisiana Gulf Coast Master Plan. I've read most of it. They are projecting over the next 50 years, this one state spending $50 billion on coastal protection, $25 billion for restoration, mostly marsh restoration, and $25 billion for structural and non-structural risk reduction measures. So a lot of work to be done over the next 50 years in in Louisiana. Texas has something similar. You might be aware of or familiar with the 2023 Texas Coastal Resiliency Plan that maps out a whole series of projects to help protect the Texas coast. The biggest single one is the Galveston Bay Surge Barrier System, also nicknamed the Ike Dike after Hurricane Ike and the damage it did to this part of the world. The project is illustrated in the figure and includes a 2-mile wide tidal gate or surge gate across the mouth of the Galveston Bay. There's an illustration of a concept design for the gates in the lower right. These are also called the Boulevard Roads Tide Gate. You might have heard that name. It includes raising the seawall around downtown Galveston by 4 feet. You think 4 feet is enough? We go back to those sea level rise plots. That'll be exceeded by 2100. So when I read this in the plan, I scratched my head. I don't know the answer, but it's the kind of question we need to think about as engineers. What are we designing for? Maybe this is a 50-year design life or something, or maybe, I don't know. And then about 40, this is really interesting, about 40 miles of sand dunes running to the south and to the northeast, as shown in the black dashed line, about 12 to 14 feet high. The current cost estimate with some escalation because it won't be constructed until the future, is about $40 to $50 billion. It'll be the biggest U.S. Army Corps of Engineer project ever constructed. The construction duration will be 20 years. But the start date is uncertain because Congress, a lot of this money is coming from the federal government, and Congress has approved money for planning, but not for design and construction. So if it takes 20 years to build, and let's say, just for the sake of discussion, you're still 5 years away from getting money to design it and build it, this won't be done for 25 years. What's the probability of a major storm coming up through Galveston Bay in that period of time? It's pretty high. So the consequences of doing or not doing projects like these are significant. And again, going with the vision of the UT department, this is clearly engineering the big. In fact, I would say this is engineering the massive. Another project in this area, a little bit smaller scale, but still one that I would say is engineering the big, is the Orange County Coastal Storm Risk Management Project. This one is funded, and as I understand it, it will start construction in 2024 or 2025. You can see the levees and pump stations in the graphic on the right that surrounds the Orange County, Sabine Lake area of the eastern part of the state. The project will include about 25 miles of levees and flood walls, 7 pump stations, 2 navigable sector gates, as shown in the upper left, to let ships and boats in and out, and a bunch of closure gates on the flood walls that they can actually close across the roads during major storms. About a $2.5 billion project, and again, expected to be start construction late this year or next year. Well, let's move on from sea level rise and storm surge adaptation to flooding. We saw that the future will have increased precipitation intensities and frequencies. This will create larger flows in our rivers and streams, and is our infrastructure designed to handle that? And when we think about rivers and streams and flood protection, we normally think about things like levees, flood walls, pump stations, overbank storage, and things of that nature. Well, the U.S. Army Corps of Engineers has a national levee database, and it's really interesting to look at it because it contains over 7,000 levee systems with more than 25,000 miles of levees in it. Think about that, 25,000 miles of levees. And the average age, more than 60 years. So clearly, these structures weren't designed with a vision towards climate change and the conditions we're expecting to see in the future. Almost hard to imagine, 23 million Americans live behind these levees. 23 million with 7 million buildings. So the value, putting aside life and health, just the economic value of what's behind these levees is measured in trillions of dollars. So in light of the conditions we've talked about, the future conditions that we're anticipating, engineers are asking questions with respect to levee systems. Is that levee height adequate to prevent flooding with more extreme precipitation? Will the levee become unstable or erode under more extreme flooding? Will there be excessive seepage through or under the levee under future climate change conditions? Do we need to create a whole bunch of additional overbank storage so that we don't push a problem downstream and flood downstream areas? Some levee systems have been evaluated or starting to be evaluated for these questions, but most haven't. In fact, it was only this past 2 weeks, but after April 1st, that the U.S. issued its first in draft form, its first national safety guidelines for levees. So there's an enormous amount of work to be done in this area in the future. One project that is under construction is the Dallas Floodway Plan, illustrated here. And this is being constructed. You can see the floodway in green with the Trinity River going through it. in blue, and the city of Dallas off to the right-hand side. And the project includes three main elements: a chain of wetlands, basically an almost 4-mile-long overbank area along the river, up to 2 football fields wide, that's used for ecological restoration and to store water during storms. And then another element called the levee raise and side slope flattening, so to increase the height of the levees to contain the 500-year flood, from the 100-year to the 500-year flood, and to flatten the riverside slopes of the levee to 4 to 1 to improve their structural stability. And then 5 pump stations, I think 4 are new and 1 is an upgrade, that have a capacity from the land side to pump 1 million gallons a minute back into the overbank storage area. Very, very large project. Again, not to belabor the point, this is at the nexus of cities, water, and energy. It's engineering the big, and most of it is designed by people like you and me. And here are all the ways we can contribute. And I'm not going to read the list, because you know the point I'm going to make, and if I read it, you'd get more bored. So, but there are a whole lot of ways we contribute. In many ways, well, civil and environmental engineers lead these projects. Well, the politicians really lead the projects. But once you get past the politicians, we lead the design and studies and all that kind of stuff of these projects. And it's a very, very important role that we play. A little bit smaller, this is Colorado River Levee Project for the city of Wharton, Texas, about 60 miles southwest of Houston. It's a project under construction. It's being constructed by Granite Construction, and Gary Johnson from Granite is here today. We see the flooding that occurred in the area in the upper left in 2016, and a layout of the facility and of the project, and then on the right-hand side, sort of a lay presentation of conditions on the top before the levees were installed, and then below after the levee system was installed. And even though this is a smaller project, I think it's $50 or $75 million, it includes 5 miles of new levees, 1,700 feet of flood wall, and widening of the channel and creation of overbank storage. So again, another project where we would play a lead role. Adaptation for transportation systems. This is interesting. Within this century, 2,400 miles, this is from the National Climate Assessment. Within this century, 2,400 miles of Gulf Coast roadways, including interstates and major state highways, are projected to be inundated by sea level rise of 4 feet. So I'll come back again. Remember the NOAA projections? Is 4 feet enough? Should we maybe be thinking about even higher levels of inundation that are going to need adaptation measures? In any event, in the coming years, we will have a lead role in protecting, elevating, and/or rerouting this at-risk transportation infrastructure. Major role. And adaptation for transportation goes beyond that. An important area is bridge safety and bridge stability. And there have been any number of recent bridge failures in the state of Texas due to flooding and extreme flows, as illustrated by the 2 on the left-hand side, the one in the upper left in Rosenberg, Texas, after Hurricane Harvey, and in the lower left, Llano River near Kingsland in 2018. So we can contribute with bridges, deck raising, substructure and foundation strengthening, scour protection, bridge replacement, and then a whole bunch of other things, just to pick out 2 or 3. Improving pumping system capacity and reliability at roadway underpasses, increasing hydraulic capacity of culverts and drainage systems, preventing saturation of pavement base and subgrade layers, an important consideration, especially where you have expansive soils, which are common in Texas. improving the erosion protection of embankments, maybe using biogeotechnics or something like that, and recognizing the potential for increased natural hazards, maybe not so much here in Texas, but in mountain states, for example, things like rock falls and landslides. We've seen several in California in just the last few weeks. And applicable to Texas for sure now after this past winter, the potential for wildfire impacts to transportation infrastructure. So, closed hazardous waste sites. There are dozens and perhaps hundreds of such sites that have been closed in place, not with the waste removed, but closed in place along the Gulf Coast. And most of these, I can tell you, were not designed to anticipate the conditions associated with climate change. So there's a real risk that many of these sites are going to need to be evaluated for their environmental protection capacity under higher sea levels, greater storm surge, and the related impacts of sea level rise. And these would be very major projects involving geoenvironmental, coastal, and environmental engineers. So on the right, you see the same map I showed earlier, just zoomed in, and I'm pointing out the location of two sites that we closed in the mid-1990s. There's one right there in Bridge City, and as luck would have it, it's right outside of the Orange County flood protection system I showed earlier. So that flood protection system for Orange County is not going to do any good for this site. And the site is shown in the lower left, and the green dike-looking areas are actually pits that were excavated down into this marsh area, and hazardous waste was placed in there back in the 50s and 60s and 70s. So these were capped and closed in place, and all the leachate is collected for treatment. But it's really uncertain how these will perform if the average water level around them is 2 feet higher than it was at the time these were designed. So this is going to have to be looked at, and I believe there are many sites that fall in this category. So this is important because we don't want this contamination getting out into the environment. These sites were responsibly closed under EPA direction and approval, and we don't want them coming back and being problems now. And there are a lot of them because Texas, for many, many years, was a highly industrialized state. I mean, it's the home of the U.S. oil and gas industry. It's got the largest concentration of petrochemical facilities anywhere in the country. So based on the waste management practices back in the day, these kinds of hazardous waste sites exist. I'm going to wrap up, just about done. Water supply adaptation. This plot is from the 2022 Texas State Water Plan. And that state water plan says that by 2070, Texas is going to need to create 7 million acre feet of new water supply capacity, 7 million acre feet. Is that a big number? I think the way you can evaluate that number is to think about what the current water supply is for the entire state of Texas. That number is 16 million acre feet per year. So you're talking about 40% of the current water supply needed as new supply. And it's needed for two reasons. Some of the current supply is going to go away. They're going to use it up, like the aquifers I talked about a little bit earlier. And then I think you all know Texas is projecting large population growth over the coming decades. And that's going to create a lot of need. So in this plot, it shows where this new supply is going to come from, at least based on the Texas Water Plan. The green lines are basically conservation. So some of the new capacity is going to come out of conservation measures. The rest is going to come out of a new water supply. And the largest category, the one at the top of the plot, is called other surface water. And this is really a potpourri or catch-all. It's basically replumbing the water supply system in Texas. So it includes pump stations, pipelines, new reservoir management strategies, water treatment systems, and other things. Well, who designs all those things? Civil engineers. The second category is new major reservoirs. And so this plan contemplates 22 new major water supply reservoirs in the state. That's a lot when you recognize until very recently there hadn't been a single new reservoir in the state in more than 30 years. And now they're planning 22 major reservoirs and a whole variety of smaller reservoirs. Most of these are only in a planning or early design stage, so there's going to be a lot of need for civil engineering input in the coming years and decades. 2 are in construction. In fact, 1 has actually finished construction, and that's shown here. This is the Bois d'Arc Dam and Reservoir in Fannin County up in northeast Texas. The impounding dam that we see in the photos, the dam was designed, I believe, by Reese and Nichols, is 2 miles long and up to about 90 feet high with a variety, it's a zone dam, a variety of zones, soil bentonite cutoff walls, soil cement upstream face. So it's a pretty sophisticated dam structure with outlet works and everything else that we see here. So the project included a comprehensive instrumentation program, construction information management systems, a whole variety of things that we do. And again, I've illustrated a couple of them here. Everything from reservoir modeling, hydrodynamics. I'm not sure if they did thermal modeling in this case, but that often is the case. Faulting, seismic hazard, design of the dam, spillways, intakes, gates. Again, a huge role for geoengineers and more broadly, civil engineers in general. And most of the work in the state in this area, in water supply, is out there in the future. It hasn't been completed yet. So I'm going to wrap up here. I think this slide and the next one. This is really a message to the UT, Texas A&M, and Texas State CE students here today and early career professionals. And I've included this plot because I'm going to make a point with it, but I'll just explain what the plot is. These are 10 NOAA tidal gauge stations around the country. The one highlighted in yellow is Galveston, and you can see it has by far the highest projected sea level rise of any of the others. And I picked this plot because it goes out to 2060. And why did I do that? Because I wanted to capture the timeline of your career. If you're in school and graduating in the next year or two, or if you're an early career professional only a couple years into your career, you're probably going to be working, if you spend your career in civil engineering through 2060. If you've never thought of that, that might be freaking you out a little bit. But if you think about a 40-year career, you start in your early 20s, you may retire in your early 60s. Many of us work longer than that. But that time frame is the time frame when all this sea level rise is going to occur. In fact, more broadly, your career will span the period when mankind's actions will determine the ultimate severity of climate change impacts on our world, and it will be the time frame when an enormous number of mitigation and adaptation projects will be implemented. These projects will create exciting opportunities for you, but just as importantly, they'll create societally important opportunities for you. You'll be helping to make the world a better place. We heard from John about Professor Reese's dedication to the profession and how much he cared about engineering and doing the right thing. And this is our opportunity to do this once again. These are great opportunities and they're important opportunities. Through your efforts and leadership, you can have a positive and meaningful contribution to society. And I think that's enormously exciting. I wish, at least as it relates to this, I wish I was 30 years younger so I could participate in more of it. And it means that your time frame, you're going to be working in a very healthy profession. So from the standpoint of job security, if you do a good job, you're going to be needed. So I think that's a wonderful thing. I'll finish. I want to extend my thanks to the UTCE geotechnical faculty for the privilege to present the 2024 Lyman Reese Lecture. I want to congratulate UTCE for your vision and for embracing the big problems of today and tomorrow. It's a noble vision, and you are needed by the world. So I think everyone involved in the UTCAEE department should feel proud about that. And as I said earlier, if you would like a PDF of my slides, I'd be happy to share them. Just email me at that address there. So with that, I conclude. Thank you very much.
We do have a plaque up here. We're going to get some pictures afterwards, but I want to thank Rudy for the inspiring words and the excitement that we should all feel as civil engineers moving into the future, the challenges we can help solve. And with that, I'd like to invite everyone to our reception outside. And I know Rudy will be available to answer any questions and talk more about these ideas with you. So help me thank Rudy again.